Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Simon Coudé and Ian Stevens with us today. Hello, Simon. Hello, Ian.
Hi.
Right.
Hey there. Well, first of all, thank you very much for agreeing to talk about your very awesome article, which we'll get to here very shortly. But Simon, let's start with you. What's your geolocation? Where are you at?
Right now I'm at the National Observatory of Japan in suburbs of Tokyo. I'm working on the ALMA project for the East Asian Regional Center.
Very
So
cool. And yes, it is at least my February 5th, Ian's as well, February 5th. And it's Simon's February 6th that we're on the next day.
yep.
How is, does Japan get snow? Is there snow?
They had quite a lot of snow recently.
Okay.
Not in Tokyo, maybe this weekend, but right now it's a very comfortable 60 degrees Fahrenheit outside.
Nice.
It's gonna go below 32
Okay.
tomorrow, so it's gonna be a pretty big shock.
Okay. All right. Yeah, visiting Japan is on my bit bucket of things to do in life. So
It's,
yeah,
it's it's an incredible place to visit.
very
Really
cool.
can't recommend it enough.
Very cool. All righty. And Ian, how about you? What's your geolocation?
I live in the Boston area. I work at Worcester State University, but I also have a research appointment at the Harvard Smithsonian Center for Astrophysics,
Hmm.
and
Yeah.
that's where Simon and I did most of the work was at the Center for Astrophysics. Yep.
Very cool. And I imagine there is snow on the ground in Boston.
Yeah, there's quite a bit. It's been it's like for us, I don't think it's hit above 40 degrees so far yet this year, and so
Woo.
it's been like we have 2 feet of snow on the ground, maybe more in places where it's been piled up, and it just hasn't been melting. It's been there for almost 2 weeks now, and it's just
Long live snowmen.
yeah, yeah, and it's not melting anytime soon either. So
All righty. And I'm in Phoenix, and we definitely don't have any snow on the ground, but we do get a lot of Canadian snowbirds coming down for the winter. But then again, we do pay for it in the summer when it gets a little unbearable come June, July. So yeah, very good. Okay, and Simon, what is it you like to do for research?
Uh, I essentially study star formation from a cold interstellar medium perspective. So
Okay.
my specialty is mostly far infrared millimeter observations of molecular clouds, protostellar cores, this sort of stuff, and with an emphasis specifically on trying to measure the magnetic field properties of these objects. So
Nice.
through the polarization of starlight, which we'll go over in a little bit more detail
Yes, we
later.
will. Yes, we will. Cool. Very good. And Ian, how about you? What do you like to do for research?
uh, so I have trouble picking a scale, but for me, it's star formation kind of at all scales. So I do things
Okay.
on galactic scales, which is a lot
Okay.
of what the survey we'll talk about today is. And I go all the way down to the scales of disk and even talk about planet formation. So
Oh, oh.
really do everything there. A lot of the stuff I do is looking at polarized light, but I do quite a bit of molecular ion observations and things like that and other continuum surveys as well.
Lovely, lovely. And that is going to bring us to this very awesome APJ supplement article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Field maps data release. Far infrared polarization in the bones of the Milky Way. And Simon and Ian, take us away.
All right. Well, first we need to acknowledge our co-authors, our many co-authors, people that have been working on this topic for longer than even I, to some extent, and of course our collaborators that were at the Center for Astrophysics. Phil, Nicole, Howard, Andres that did a lot of work too. Everyone contributed significantly to this paper, so we wouldn't be here without them.
Very nice international collaboration for sure there. Very nice. Cool. All right. Good shout out. Okay. Let's go ahead and get into it.
Okay, so I kind of just want to introduce the survey, just kind of the motivation of it. So, the a lot of the telescopes, especially Herschel, kind of showed that star formation in the Milky Way primarily occurs in filamentary structures. So we see all these big filaments, and that's where they are. The highest mass ones tend to form in what we call the infrared dark cloud. So maybe you can just check out Figure 1 real quick, just to show kind of what
Yeah.
an infrared dark cloud looks
Let's see
like.
what an infrared dark
Uh,
cloud looks like. And
So,
there we go.
it's kind of in the definition. It's you have a dark cloud in the infrared. So this is a Spitzer image showing you what an infrared dark cloud looks like.
Nice.
So we have noticed that there's some certain kind of filaments that are particularly long and dense.
Uh-huh.
They're called the bones of the Milky Way. And when we say long, we're talking about between 20 to over 100 parsecs in size. So
Wow.
60 light years to 300 light years, these huge things.
Uh-huh.
And so we call them the bones of the Milky Way because they're these massive velocity coherent filaments that
Okay.
trace the dense spine of the galactic plane.
Cool.
The typical radius of these things are between about 1 parsec and 2 parsecs. So in kind of the
Yeah.
smaller star forming regions that Herschel did, the Gold Belt clouds, they're more
Mhm.
things that are around, zero point 0.1 parsec or so. These ones are, these huge filaments are thick, but they're so long. They have these huge aspect ratios.
Okay.
And so um, these really are the longest velocity coherent dense structures that's associated with star formation in our entire galaxy.
Cool.
Okay. And so, the bones lie close to the midplane of our galaxy,
Mhm.
often along the spiral arms. So this is a place where gas collects in the magnetized spiral potential.
Yep.
And these things being so big, it's not easy to make huge maps of them. And telescopes like Planck, who did polarization, they can't resolve these. And
Yeah.
so that's really what motivated this particular survey, the field maps. So there's 18 known bones in the Milky Way, and we mapped completely 10 of them. All
Nice.
right.
Okay.
And so we think magnetic fields can guide flows and they can slow down gravitational collapse, influence fragmentation, early evolution of star forming cores. So that's why we use the SOFIA telescope to map the magnetic fields about all of these. So until the field map survey, the magnetic field morphologies were essentially not constrained. And so now field maps kind of provides the first systematic polarization maps across these enormous structures, allowing us to kind of study how magnetic fields regulate their evolution.
I'm with you. Good. Let's see, and the colors here have to do with the classes. Okay. Very good.
Yeah.
And that's the Herschel beam size over here.
Yes, we
500 micron.
Yeah,
Uh-huh.
yeah. So we're showing a lot of the circles. We're showing a lot of the young stellar objects, and we'll get back to this figure. I think maybe we should we kind of introduce the survey, and I think we got a
Yeah.
little bit more introduction. I'll let Simon kind of talk a little bit more about that.
yeah.
Okay. Let's climb
So
back up to the intro a little bit. Okay.
right. So trying to measure magnetic fields is quite a difficult task in astrophysics.
Hmm.
And one of the best ways that we have is doing it through Zeeman line observations, but that turns out to be extremely difficult, and very few places in the, the galaxy um, uh, are good, are bright enough essentially for us to do that.
Right.
But thankfully, we have an interesting alternative, which is the polarization of interstellar dust itself.
Okay.
So through well, through physics, really. So we, in the past, since we've begun studying interstellar dust, we've learned a lot about it. But we discovered very quickly, and I think it was in the 50s even, that that dust grains in the interstellar medium polarize starlight essentially. So first in extinction and absorption,
Yes.
and that was a bit of a mystery, trying to figure out, well, why is that? And the most likely explanation, which was then supported by a ton of theoretical models, was that interstellar dust grains tend to align themselves perpendicular to the ambient magnetic field. And one of the most successful ways to do that is a mechanism called radiative alignment torques.
Yes.
So dust grains tend to be a lot of times, a lot of the dust grains that we're observing and the interstellar medium are made of some kind of silicates, for example, and it's a paramagnetic material. And as you spin these little asymmetric dust grains, you end up with the momentum being aligned um, with the magnetic field through something called the Barnett effect. So what this does essentially is it gives us a probe of the magnetic field, at least in the plane of the sky, by measuring the polarization of these objects.
Cool.
We can do that in the
Yeah, so
yes.
just to be short, if you know my arm's the magnetic field and my phone is the dust grain, they align, oh my
Yeah.
gosh, the chopping of the thing.
Disappears into the background.
Yeah, it disappears in the background. Let me see if I can get that line. So it's kind of perpendicular to the magnetic field.
Right.
And so you get more stuff along this axis than this axis, you get polarization along that direction.
Mm-hmm.
So the polarization, and that's for we're talking specifically emission. We talked that you can get absorption too, but what we're doing in this paper is emission. So you get more stuff emitted along this axis than this axis. So that because you have more stuff emitted there, you get polarization perpendicular to the magnetic field that's threaded up and down.
Very cool.
And so we just flip all of our polarization vectors, and that measures the magnetic field direction.
Very good. Cool. That's
And
great.
there are other
demo.
ways. Yeah.
Yeah.
There are other ways of aligning dust grains. The physics is different, for example, in protoplanetary disk. For molecular clouds, we are quite certain that this is the most likely scenario. So we can get information about magnetic fields, which is very difficult. But even then, that polarization is only a few percent, for example, of the thermal dust emission. So it's a very weak signal still, and so you need very sensitive instrumentation or a lot of time both ideally
both
to make these observations. And that's why it took so long for us to be able to do a survey like the FIELDMAPS survey that we did with Sophia, because we needed a polarimetric camera like Outplus in the far infrared, which is where the dust thermal emission peaks, so it's the brightest there, to really have a chance of measuring that polarization, the polarized signal, and then get the magnetic field directions.
Cool.
So I guess now is a good time to explain how we chose the targets essentially for Sophia.
Okay. Let's see. Targets. Sure.
I think that's 2.1.2. No, 2.1.1, sorry.
Yeah. Let's see. 2.1, we're talking about Sophia, and we're going to slide down target selection. Here we go. 10 of them.
Yeah, so again, Sophia, observes at multiple wavelengths. It happened that, first of all, 214 microns all we use for the survey because it happens in the galactic plane.
Yeah.
That's where we see these things in emission, and with the biggest contrast with the background that we see in the Milky Way. I mean, all of these are along the galactic plane, so there's a lot of stuff there, and you need to have something with high contrast.
Yep.
And so I mentioned earlier there's 18 bones that were identified essentially in Catherine Zucker's 2018 paper that you have listed here. And so and we picked 10 partially because it gives us a lot of statistical prowess, and with these we have these huge things, so you have a lot of statistics on just one bone, but getting a lot of different ones together. And then also these were the ones just had high contrast. Some of the most well-known bones in the Milky Way, there's one called Nessie. It just happens to not have much contrast, even though it's the biggest one and been awesome, but it's just not that bright compared to the background.
Okay.
And so it's things that we could map fairly quickly and do. And so we pick these 10 bones. Well, we had kind of a pilot first. We looked at the snake and also filament 5, and we looked at these two and saw that it could be done. And we'll talk a little bit more about these targets. And then we did 8 additional ones. And that's ultimately what it worked. And what's so great is that, like we mentioned, usually it's really, really hard to get these observations. We have to have a lot of time and to get these small signals. Well, in some ways, we didn't have to have much time with these because they're so crazy bright with the contrast that with the Hawk Plus instrument, they're detecting the polarization right away. But
Right.
in some ways, it's the field of view that matters more. So we need multiple
Right.
pointings on these that we put together,
Yeah.
and we splice those together. And I think Simon, maybe you can remind how long the integration was on each of these. Do you recall what that was right away?
Oh,
For
that's
each field that we
for
had.
each individual field. So whenever we would look, it would be a field would be, I think, 10 minutes. We would repeat it at least twice,
Ooh, okay.
if not more, depending to reach the required sensitivity. So a single target could be easily a couple hours
Oh,
Yeah.
wow.
observing
Yeah.
time.
Okay.
And I
And
mean,
yes.
you see all these targets here, and how long we had to do them varies quite a bit. So if you look at that the column that says length in
Hmm.
parsecs, so
Hmm.
right there you can see they're very different in lengths. So from kind of 10-ish parsecs, most of them more towards 20, but or more,
Really
all the way
long.
up
Yeah.
to 76
Yeah.
parsecs. And so we got these pretty huge lengths that we have. And so some of them, especially that G24, and we'll get to its beautiful map later, but it just took a lot of pointings. I can't remember
Oh, yeah.
right away because we kind of changed some of the mapping strategy midway through. To use on the fly mapping, which I think we might talk about in a bit. But
Okay.
something we spiced a lot of observations and they took a lot longer. Things like uh, filament 1 and filament 8 did not quite take quite as long. Okay.
8. Yes. Yeah. Yeah.
Yeah.
Definitely smaller, but
Okay.
all not.
So the other thing that to say about these, I think is worth it. Just put things in context. Yeah. Again, the widths are about, like I mentioned, about between a parsec and two. And
Yeah.
the masses of these things, as you can see listed here, if we talk about all bones that we know of, they're typically somewhere between about 3,000 solar masses to
Yeah.
about 60,000 solar masses. Almost 100,000 solar masses. So these really large bones. They're really going to create we know a lot of them are already creating high mass stars. So they're creating high mass stars, low mass stars, making, clusters of stars. But, it's in a big filamentary structure rather than this compact thing. How the things density disperse, et cetera, I think that's a topic of discussion. But you see the masses vary quite a bit here.
Yeah.
And they have, column densities somewhere around 10 to the 22 centimeters to the -2,
Yep.
and some densities, we're talking about 1,000 or so, 1,000 to I think it's up to 10,000 centimeters per centimeter cubed.
Okay. Okay.
And so these things, again, one more parameter about them is they're really cold because there's not much star formation yet, and so we're talking about just a little below 20 Kelvin most of these
Okay.
bones.
Okay. Hmm. Very cool. Nice.
So
Okay.
now that we have our clear targets that we can do with Atlas, well, let's talk about Atlas and Sophia itself. So we mentioned it quickly, but Sophia was the Stratospheric Observatory for Infrared Astronomy, which was a NASA mission with uh, in partnership with the German Space Agency, essentially,
Okay.
to have a modified 747 airplane where we literally dug a hole on the side and put a 2.7-meter telescope on it. And
Hmm.
the idea for this crazy mission was to get above 99% of the water in the atmosphere.
Yeah.
And the reason is simple. Water absorbs a lot of far infrared energy.
Mhm.
So a lot of the light that comes from these very cold regions just gets absorbed by the atmosphere. And if we want to observe this very important regime
Gotta go up.
uh, of dust emission, essentially the peak of the thermal dust emission, well,
Uh-huh.
either you need to go to space, which is very expensive and complicated, send balloons, which have their own risks, as we've seen a lot of times, or do our airborne astronomy. So Sophia was the attempt at using an airplane to do this. And in our case, it worked very well. So,
Cool.
Yeah.
um,
And of course, Sophia is just awesome, as you have highlighted. There's like you can
Get the
repair
whole
it,
thing.
you can add more coolant, you can make new instruments, and you can do we could do all kinds of stuff. And it was terrific while it was active. But
Right.
and so Herschel was a very short mission, for example, and Sophia had a lot of capabilities that Herschel could not do.
Right. Okay.
Yeah. And the big
so
one is that Hawk Plus camera. So I'll let Simon
Yep.
talk about
yeah.
that.
Yep.
So since we could switch instruments, yes, Outplus was became one of the facility instruments. It really started doing a lot of heavy lifting observations in 2017, 2018 when I started working there because disclaimer, I did work as an instrument scientist for
Oh,
Sophia
okay.
for a few
Cool.
years before the mission was told. So I was working directly with Outplus, and I even took a lot of these observations myself on the airplane.
Very cool.
So it's really artisanal made research.
We're deeply into this one. Yes.
Yeah. So Outplus, it
Okay.
multi wavelength parametric camera. Was the main bands were 53 micron, 89, 154, and 214. And as Ian mentioned, we focus mostly on the 214 micron here to get the best sensitivity for
Mhm.
our research. And yes, table one shows some of the important
Mhm.
um, characteristics of the observations, the beam width, the wavelength, the field, the size of the field of view for in polarization mode,
Right.
and the detector and pixel sizes.
Mhm.
And the field of view essentially was the way Outplus worked was that we had several detector arrays in the focal plane, essentially, with an half-wave plate and a polarizer in front. So what we would do is whenever we would observe a source, we would rotate the half-wave plate to 4 different angle positions.
Okay.
So perform observations with one, switch it with the other, and repeat that as long as we needed to reach the sensitivity. And then we would have all these individual angle positions that we would get into the data reduction pipeline, calculate what the on-sky polarization was, the Stokes parameters, Q and U, specifically the
Yes.
linear ones.
Mhm.
And from that, we can construct these polarization maps and these magnetic field maps.
Cool.
So there
Wow.
were challenges as
Always.
with any observation in astronomy. There was one flight where there was an error on the pointing of the telescope. So there's a whole appendix, which I think is Appendix B or C. Maybe
Uh, yeah, do you want to go
we
down there? You want to go?
um, it might be D. Well, for this one, it's I'll just mention it briefly, but we had to do corrections for the pointing on one of the sources,
Yeah.
and we managed to do it very accurately, which
Nice.
was
Steve.
very happy with because it would have been a shame to lose data just because you don't know where you're looking at. So thankfully, we managed to salvage that issue.
Yes.
But as Ian mentioned, we had done some pilot projects, pilot studies of some of these bones, and
Mhm.
filament 5 specifically is the only source that we had where we use 2 different observing modes.
Okay.
So Appendix A talks in very long details about the characteristics of the observing modes for Sophia, for Atlas specifically. The 2 main ones were Chopnod, where you essentially look at the source and move the secondary mirror so that it looks at NP sky,
Yeah.
and you use that to get rid of the background.
Yes.
Because in the far infrared observations are what we call background limited. So we have to get rid of the atmosphere, the light that's emitted by the atmosphere to get the astronomical signal.
Yes.
But the other alternative is scan mode, which ended up being the mode that we used for all of the observations in the FIELDMAPS survey except for one source.
Okay.
And that's just moving the primary mirror essentially around the target. And as we move the telescope, the signal of the atmosphere varies more slowly than the astrophysical signal. So essentially,
Oh,
you
yeah.
filter
Okay.
for the background and you remove it this way. So there are advantages and inconveniences to each technique. The chop nod technique, if you can get a good off position, is very good at removing the background accurately, but it's extremely difficult, especially in our own galaxy, to find a background without any emission because there's dust everywhere. So
And you need
scan
a
mode,
symmetric chop nod. So you need to
yes.
get on both sides. And so you need empty things that are on both sides of the bones, which wasn't easy to find. So
Yeah.
Right. Okay.
And actually, that now would be a really good time to go to Appendix C, I think,
Yeah, let's go down
specifically for that.
to, I think we got a link to it right here, Appendix C. We'll get
Yes.
there very quickly. There we go.
So we spent a lot of time checking essentially how the two different observing modes work for filament 5. So I think it's the figure that's on the next page, maybe,
Okay, just
um,
getting a sense
which is
there. I love the detail here. It's fantastic. Okay, very good. And let's slide down
it's
to the
figure 18.
here.
Yes, this one.
Yes, let's zoom
So
out a little bit to get the global.
yeah. So on the top left is the chop node data, and the other figures are essentially by varying the different reduction parameters. So that's
Okay.
another whole thing that we explored, how to calibrate the data reduction pipeline to get the most out of our data without creating artificial artifacts that weren't physical.
Okay.
And actually, where you have your cursor there a minute ago, like just at the bottom of that panel, there's like a white spot in the middle. So that's exactly
Ah,
what Ian was mentioning. Like this, there was
that was good.
an infrared source in that off position, and so it appears there as a negative signal. Uh,
Ah,
Fortunately enough, we
okay.
in the scan mode observations,
Oh, yeah, yeah, yeah,
you don't get this issue, and we could still show that it was a very good agreement, mostly
yeah.
between um, the two observing modes. There are some. There's a lot of details about like depending on some of the parameters that you use. Sometimes you have a detector flux jump that we call, like it's
Right.
just
That was
an
it.
instrumental effect, and if there's not enough astronomical signal, it can shift the whole background. So we discussed that, how we corrected
yeah,
for that in this very specific case. So
yeah,
filament 5 was,
yeah. And just
yes,
pause for a second, just because we haven't explicitly said it yet. What you're seeing, these little red
Yes.
vectors, they're
Yes.
not true vectors because they don't have a particular location it's pointing. But that's the polarization I'm talking about
Okay.
with what I was doing with my phone earlier. And those the polarization directions basically measured, everywhere based off the resolution. We kind of plot about, it depends on the image, but about two per beam or so.
Okay.
And so the resolution you see in the bottom left, that circle, it's about 18.7 arc seconds. That's the smooth resolution. And so
Okay.
these bones, they're at different distances. They're from a couple kiloparsecs away to almost 10 kiloparsecs away. And
Okay.
so the resolution, spatial resolutions we're getting is somewhere between about zero point 0.1 and zero point 0.5 parsecs is what we
Okay.
have. And again, just to remind you, the bone's width are about 1.5, 1 to 2 parsecs in size. So we're able to resolve all these bones
Beautiful.
with this particular resolution. And so,
Beautiful.
yeah, and so we're just seeing a small, section of one of these bones where, of course, we did both the chop nod and scan pole. And so,
Huh? Uh-huh. Very
and
and so when you're saying there's a good agreement, we mean the magnetic field we're measuring and the chop nod agrees with the magnetic fields we're
yes.
getting a scan pole.
There you
Yeah.
go. Verification. Yep.
Yep.
Hmm.
Yeah, so
Cool.
actually, it would be a good moment to go to section 3.2, which we actually
Okay.
define the polarization properties of these objects.
think we're
So
here.
with the equations, we show what all the Stokes parameters, IQ and U, which contain the information about the polarization of the light, incoming light, are defined in the coordinate system that we were using, which is also another appendix. But we use a galactic reference frame for all the observations, so we had to convert the data from the celestial coordinate system that we were using to galactic, but the mathematics is the same in this case, and we can get the two important quantities, the polarization fraction, so essentially how much of the light is polarized, and the polarization angle. So that's equations 4 and 6. Yeah.
Yes.
So the very, very important thing that we need to get the polarization orientation is the angle. So the arctan of U over Q. So that tells us what the polarization orientation is. And as Ian mentioned earlier, because the polarization is perpendicular to the magnetic field, you add 90 degrees, and then you have the plane of the sky component of the magnetic field in these region.
Nice.
Okay. And I think the table 3 just above, and that that gives you the number of positions in the maps, the number of pixels or that had a significant detection of polarization. And it's worth noting here that 20 years ago, like not even 20 years ago, 15 or 10 years ago, like these numbers would have been incredible. Like people were celebrating, I think, 12 or 10 or even just one.
Even
and now we have
like
hundreds of beams of detections of
it's
polarization.
very impressive. Very nice.
So yeah, it's I think one of the most I wouldn't say thorough, but like complete surveys of filaments in a way and polarization that exists. There's a lot of data now, but it's still limited to some star forming regions that are either nearby or very bright or far away. And this thematically, essentially, like looking at the bones of these long filaments in the plane of the galaxy, that survey is well, essentially the only one, as far as I know, that did that.
Yeah, this is a magnum opus. Magnum opus.
Yeah, and just really having this many, measurements in that field on any cloud is just it's ridiculous. I mean, just have so many, and it's just
it's awesome.
There's nothing really like it. Sophia just did a tremendous job, and like I said, these things are bright. It's just they're so well mapped, and there are not many big filaments like this that data exists for. In fact, this is them.
It may not for a while now that Sophia is no longer. So very cool.
Well, there's still hope for the future. We'll get there.
We'll get there. We'll cover that future. Yes, we will. Okay.
So let's jump to figure 2 then. Let's show what these observations look like. We had a glimpse at filament 5 in the appendix, but so this is what it would look like, especially in this case, is for filament 1. So to describe a little bit, the top panel is the magnetic field direction. So that's why all the little vectors have the same length. That's just to show the direction of the field. That's to really help us identify what the field structure is doing in the plane of the sky. And we compare that. So the red vectors are what we measure with OCTPLUS. The blue vectors are the Planck data. So Planck was this incredible mission that mapped the entire sky in the 500 millimeter, 7-meter regime. And it was a cosmological mission. So they wanted to look at the microwave background. But unfortunately for them, fortunately for us, there was the galaxy in front. So they had to get rid of that. But it makes it so that they have a very complete map of the dust emission in their galaxy at a very coarse resolution. So we're talking arc minute
Yeah.
level resolution compared to octos. So not enough to see the field in the filaments themselves, but enough to see what the structure of the
Little,
galaxy, the
or
structure of
more
the magnetic field of the
localized.
galaxy
Yeah,
looks
larger
like.
scales. Uh-huh. Uh-huh.
And so for each one of our filaments, we looked at the Planck data. We plotted the vectors, we looked at the orientations, and we compared the structure
Huh.
of the out plus vectors to what
Huh.
we were seeing at larger scales.
Yeah, interesting story to tell there, it looks like.
And yeah, and then again in this the top panel, the grayscale is the Herschel column
Uh-huh.
density map. So
Yeah.
this is what all of these targets were observed by the EIGAL survey with Herschel, which created a very thorough data set for these objects. And we did some work to recalculate some of the physical properties of these, so the temperature, the column density, and we use the column density here to identify essentially which regions are denser than others. And the white contours at the Stokes eye, so the total intensity that we measured at 214 micron.
Nice.
Uh,
Yeah.
and so the bottom panel is a very similar map. But instead of showing the magnetic field orientation, we show the polarization vectors. So the original
Yep.
polarization signal and the length of the vectors is how what the fraction is. So
Aha.
the more of the light is polarized, longer the vectors are.
Yes.
And
And
there's
clearly you can see the polarization's 90 degrees from the
Yes.
magnetic field direction on top. It's all rotated 90 degrees. That's
yes.
what,
Yes.
what we did.
Yes.
Uh,
So
Yes.
And in this
Uh-huh.
case, the grayscale is
Uh-huh.
the same as the white contours. So it's to create an easier reference for reading the
Gotcha. Yeah. Like
each
that.
plot.
Wow.
And we did this for every single filament. So and you can also see we identified the position of young stellar objects that we found. So that's work that Nicole Carnett did. She went through every single one of these filaments and dug through the catalogs and got the
Wow.
YSOs and that were found with Spitzer and all the masers. So we have all of that here.
yeah,
Nice.
but
Nice.
that's
So
all the little stars that you can kind of see in that top panel.
Mm-hmm.
It's
Mm-hmm.
that kind of
Mm-hmm.
green and blue stars that represent young stellar objects at different
YSOs.
evolutionary ages.
Yep.
Yep.
YSOs. Uh-huh. And you even have a little
so we have
polarization.
10 sets of figures
Okay.
for with all the data. Maybe Ian, is there a specific filament that we should go over? Mention
Uh,
some of the
yeah, let's just scroll through slowly through them. I think we'll
Sure.
probably maybe
Yeah.
stop a little bit on
Go.
filament
We're gonna do a
5 and the
slow movie.
snake. But yeah, just I think it's to me one of my favorite things to show even in any talk. It's just the wealth of data we have. And so just go ahead and start scrolling through each image slowly. So let's just get to
Okay.
filament 2.
Let's do a slow movie. And this one
Yeah.
is big
So
filament.
filament two. So, this is one of the larger ones, right? So, filament two, you can see this took many
Ooh.
different pointings to do,
Uh,
all in scan pull all stitched together. This thing is what was it? I think this one is about 40 parsecs long. And it's a lot more active in star formation. You can see how
yes.
many stars there are, just
Mhm.
crazy. So we're really getting bones at many different evolutionary stages. And you can see some of them are a little more, all this is in galactic coordinates, as you can see in the axes. Some of these are more, aligned with the magnetic field, or sorry, aligned with the galactic plane. Some of them
Yeah.
are a little bit getting a little bit off it. We think there's some galactic shear that might be happening with some of these. And so, um,
What is the gray curve here? Two.
Oh, that's the limits of the Octus observations.
Got it.
A recommendation from the reviewer that we like very much. So
yeah,
Okay.
yeah,
Yes. Yay! The peer
yeah.
review process work. Yay.
Yes. Yeah, yeah. So, like again, this is still the same image, top and bottom,
Mhm.
or sorry, same source. But you can see that clearly that contour goes with the footprint that we see in Hawk Plus, the Stokes eye on the bottom. So, all right,
Yes.
so let's just keep on scrolling through them.
Let's just do a slow movie here. And we got some interesting tables there. We might come back to those. And this is
Yeah.
now filament number 4.
And so again, just a lot more. This is a smaller one, but the signal noise is great. There's just so many vectors. We're getting
Ooh,
more of kind of the
three.
diffuse submission, even
Yeah,
with this
yeah.
particular one.
Wow.
And so let's keep on going through them.
It's okay.
Kind of quick
So
look through
slow
them.
roll, slow roll.
Filament 5. So this is the one
Five.
that we were checking at earlier in the appendix. That we looked at that kind of blob that's towards the top there, except for it was in equatorial coordinates that you saw in the appendix. Now it's
Cool.
turned around into
Yeah, yeah.
galactic
Or
coordinates.
rotated LB. Yeah,
The
yeah.
coordinates of our galaxy. For us high mass star forming people often like the galactic coordinates, and so.
Oh, good. I like either coordinate system is good with me.
Yeah. And we have a colleague that has analyzed this source quite a bit as well, and so we're hopefully preparing something for this source as well. But let's just keep going on through. So let's go to the snake.
Hey,
So the snake
there
is
we
the
go.
common name. Filament 6 is kind of the catalog name. This one in many ways started it all. So this was a lot of the all these bones started getting identified by eye, kind of with Spitzer, but this was even dated before Spitzer when this got identified. And so
Cool.
this is a pretty iconic one. This one was a little bit different. This was one of our pilot sources we had. So this is the only source we had that we did chop nod only for it. And
Yeah.
so
Okay.
and so
Sounds
scan pull actually helped signal noise quite a bit because you're scanning and you're basically getting signal most of the time and use some background at the end. And so the snakes just would have been awesome, better if we used scan pull eventually, but it's still just excellent data
yeah.
with it as well. And we saw a lot of the magnetic fields that kind of perpendicular to this particular bone. But we might talk about that more later.
Okay.
All right, let's keep on, just
Lovely.
go
We
through the rest.
bone 6, and then we'll take a look at filament 8.
Filament 8. So filament 8 was the one that we didn't map the entire one. So this is just a small section of filament 8.
Yeah.
So it happened that Sophia's end of life happened before we could complete this particular observation. So we have the least amount towards this one. But
Part of it. Part of it.
but the one we have, we got quite a bit of vector stores. But let's just keep on scrolling through. Filament
One,
10. That's a
8. Oh,
another
got filament number 10. Okay.
10, yeah. And
So,
so filament 8 and filament 10 actually showed another great power of Sophia that you can't get for ground-based stuff is that you can target both the northern hemisphere and southern hemisphere. So
yay.
filament 8 and filament 10 was the New Zealand flight series from
Okay.
Christchurch.
Sophia.
Yeah.
Yep, out of Christchurch. And so,
Yep.
I think Simon specifically took these observations.
Yes.
And so just more excellent ones. Film 10's another crazy one with, when I say crazy, but has so much star formation happening nearby. There's just like a ridiculous amount of star formation that, um, with it. So you see all the stars on the top panel.
Yeah.
And
It was
then,
one of
Yeah.
those, if I can go very quickly, it was one
mhm,
of those choices that we had to make once we started observing them in New Zealand and we realized that filament 10 was going to be a lot brighter than filament 8. We prioritized finishing filament 10 and getting it all the bone observed. And
Yeah.
then we still managed to get the brightest chunk of filament 8. So it
Excellent.
was a difficult choice to make, but at least we got a lot of good science out of it.
Mm-hmm. Mm-hmm. Beautiful.
all
Nice.
right. And then we got three more, I think, still.
Yeah, we got a couple more. No hurry.
The- Yeah, so
G24.
G24. So love this one. So in many ways we try to make it the vectors legible by spacing them quite a bit, but this is our biggest source that we have as far as biggest map. This thing's 76 parsecs long. It's just
Yeah.
huge. So
Yeah.
it's so many vectors towards this thing. And again, we space
Cool.
them very nicely just so we could see what's happening. But if you really want to get
Yes.
down the resolution, it's just so much. And
Yeah.
you can see my companion 2025 paper where I actually start plotting all those and I literally put it there. So you can zoom in to try to make more sense of individual regions.
Yeah,
But
yeah, yeah. We'll
so
zoom in on one.
Simon's is more of the global picture that you can see kind of what's happening. And it's not these. What you're noticing towards a lot of these bones is not a simple morphology of everything perpendicular to the bones or parallel. There's a lot of stuff happening, and talking about all that's kind of beyond exactly the scope of this paper, but we might briefly talk about that. But ultimately, there's maybe a slight preference for things to tend to be perpendicular towards the bones, the magnetic fields be perpendicular to bones. When I
Yeah.
say slight, some bones you don't see it much at all, but most bones you see a slight preference, especially at the highest common density, that you get a little perpendicular with
Yes.
the bone.
I
And but
dark.
uh,
Right.
yeah. And to
Yes.
really do it, you have to take
Yes.
into account projection effects too, because we're just seeing the plane of the sky magnetic field. And
Correct.
so you can kind of compare it to Monte Carlo simulations to see what you would expect for the distribution of magnetic fields to be for some with the Monte Carlo simulation versus what we actually see.
Mhm.
And we see a preference of them to be more perpendicular than parallel. So,
Yeah, I think that's even in
um, all right. And so let's just
Yeah,
go
and we
through
will. I will put a link to that other paper in the description below this video, people.
Okay, all right. And let's just check G47 and G49 as well, the last two.
Page
So, yeah,
47.
so G47 was the first one that we actually had an individual publication about. So that
Yay.
was Steven Siddall 2022.
Mhm.
This one we see quite a bit of fields that are perpendicular, but not everything's perpendicular.
Ooh, yes.
And so it's a beautiful signal towards this. So we got it traced pretty well throughout the entire bone. Let's go check out G49 too. G49 is another one I just really, really like.
Right.
It's
Cool.
another,
I'm just absorbing the beauty of
you
that one.
the wealth of the
Um,
data.
yeah, yeah. Okay, and then G49.
Yep, yep,
Okay.
another big one with a lot of measurements towards it.
Yeah.
And so again, this thing is another huge, pretty big filament, G49. We're talking about getting close to 60 parsecs in length. And so again, we had to have some very nice spacing here so we can see kind of the global picture of what everything happens of the magnetic field vectors. But again, if you actually go into the data, you can zoom in regions and you have even kind of more magnetic field vectors than what you even see here.
This one has
Um,
green squares labeled.
Yeah.
What are those?
So we wanted to look at as a proof of concept anyway at individual subregions. So that actually goes well with the next figure, figure 12
Ah,
and 13.
that was not planned. Okay, so we've got particular marked out. We're going to drill down on A through D. Okay, so let's go down and
It makes more sense if you look at it in the perspective of figure 12. So we did histograms of orientations for all the vectors for each of the bones.
yes,
And one of the things that really came out is although there are preferential orientations in some cases, sometimes there's so much variation in field orientation, it looks like
mess.
it looks like a mess, like it looks like it's completely random.
Right.
But looking at the maps, it doesn't look random, right? It looks like there's very clear structure. So those little boxes where essentially zoom in some regions. The actual histograms for these regions are in the appendices,
Okay.
but it was to illustrate that globally, the magnetic field in these bones might be complex, but locally, they're actually really well ordered. There's
Nice.
a very small dispersion.
Okay.
And that's important for, again, the companion paper to this work, Stevens 2025, because that's how you measure the magnetic field strength through something we call the Davis-Chandrasekhar Fermi method.
Yes. Yes. Hmm.
And so the more ordered they are, the stronger the magnetic field is. And so these things, even though there's a huge dispersion on, like as you said, these large scale, at small scale, the dispersion is not that big, at least in a lot of areas. And
Yeah.
so we actually do find that doing these estimates of the magnetic field strength, the magnetic fields are fairly strong. At least the magnetic energy is comparable, and sometimes is even more than the gravitational
Okay.
energy, which says that ultimately that magnetic fields are quite important to the star formation process, at least at these
Absolutely.
scales.
Absolutely. Okay,
And
that's 1 through 8, and then we go 10, and then the G24, 49, 47. Okay.
yeah, and then in figure 14, we decided to just
Stack
take
them.
all the vectors, all
Stack
of
them.
them, stack them together and see if there were preferential orientations. And
Okay.
so when we say that the magnetic fields tend to seem to prefer being perpendicular to the length of the filaments, well, this is essentially how we find that.
Uh-huh.
Because all of these filaments are parallel to the disk. And in this case, it's a polarization angle, so you need to rotate it by 90 degrees to get the magnetic field orientations. But there's a preferential for
Yeah.
the output data. There's a preference for the magnetic field vectors to be perpendicular to the length of those filaments, and so to the
Interesting.
galactic plane, which is the opposite of what we
Yes.
find with Planck. Planck
Yes.
finds it to be parallel
On
to the
larger
galactic
scales,
disk.
though. On larger scales.
Yes. So there's a lot of caveats to that, like on analyzing the Planck data, we integrate along the line of sight everything, but there's a
Yeah.
clear change in field orientation at some point, at some scale, between the galactic field and the field that we measure at smaller scales.
Yes.
And we illustrate that in figure 15.
Okay, let's slide down. I love that histogram. Very nice. Let's slide down to 15. Ooh, comparison. Here we
So we compared the Planck and Alpla's mean values. So we took the averages of these distributions,
go.
and the
Okay.
gray lines are the dispersion. So you can see that there's a very wide variation.
Mm-hmm.
But in general, what we see is a magnetic field for Planck that's very, very close to parallel to the disk.
Yeah, right at
With
90 degrees right there, 90
yes,
that you see based off the y-axis, 90 degrees. That's you see Planck, all the Planck stuff, basically, that's the y-axis. You can see
Uh-huh.
almost everything's right near that red dashed line going horizontally.
Yes.
So that says, yeah,
Yes.
for Planck, things
Yep.
are,
Yep.
yeah, nice, parallel to the galactic plane.
But
but for Alplas, there's a larger dispersion,
uh-huh.
but they're a little farther away from the middle vertical red line. So it's
I'm with you. Mm-hmm.
complicated because these are magnetic fields that have a lot of structure, which it was an important find of this survey, saying that they could be locally ordered, but and the length of the filaments change a lot. But there's this clear discrepancy between Planck and non-Planck, so that we can that we measured and we can show here.
Mm-hmm.
So that was, I think, an important takeaway just from doing very simple statistics
Very
of the
nice.
polarization angles.
Very nice. Right. I'm with you. Mm-hmm. That's a great figure. Mm-hmm.
And so that's essentially it for this paper about quantifying the magnetic field structure. We're gonna have a quick look at figure eight, not figure eight, equation eight, sorry,
Yeah, all good. All good. Let's back out and
which is
we're
yeah, a little lower.
lower, lower. Sorry. Lost the
This there, there,
colors.
there.
Eight, eight. Oh, here we go. Yeah, yeah. Okay. Mm-hmm.
So that's it's mentioned briefly in this paper, but again, the real work is done in the companion paper to this. But this is essentially the form of the Davis-Chandrasekhar Fermi equation. So
Yes.
we're not going to do too much detail. The idea is that you can use the dispersion of polarization angles
Uh-huh.
and a measure of the turbulence in the medium. So
Yes.
through line widths, for example, to get the Avin speed, and if you know the density, the magnetic field amplitude in a given region.
Cool. Yes. Mm-hmm. Cool.
Uh,
Okay. Main takeaway is that the plane B is inversely proportional. Yes. Right. Okay.
Yep.
Cool.
Yeah. And so what people commonly do with this is to compare the magnetic field strength to what the critical magnetic strength is expected to be. And you try to see, okay, well, are magnetic fields important for star formation? And so the
Right.
companion paper and also this 2022 paper that just did G47 is showing that,
Uh-huh.
yeah, the magnetic field strengths are quite strong. And it was kind of unexpected that I thought that we were getting something called a critical parameter, which is that little
Ooh.
lambda value right there that's coming down.
Uh,
We often see it less than one, and less than one means that magnetic fields can help support the cloud against gravitational collapse.
yeah.
And so if it's greater than one, well, things can collapse. And so we find a lot of areas have, less than one, and a lot of times significantly less than one, which um, this technique of measuring field
Yep.
strengths has a lot of uncertainties, but if we're that far below one, magnetic fields are important,
Very
and so that's clearly what's shown with kind of the companion paper.
cool. I'll put a link to both those papers in the description of the video. Okay, awesome.
And importantly, in regions where we see signs of star formation in the bones, we find magnetic fields that are small enough to allow star formation. So there's a
Well, okay, yes. There's some
self-consistency
consistency there, yes. I was
yes,
gonna say.
it makes sense. The star forming region is massive enough to form stars. It's
Thank
a
you.
very important result.
Yeah, yeah, but the
Another
magnetic fields
question.
probably make these a lot longer lived than we expect, and that's the big thing.
Exactly.
And
It holds it
and
up
there
for
are some
longer.
unknowns. We do
Right.
see star formation. You see this star formation, so that means it had a collapse somewhere. And there's kind of a question, almost a chicken and egg kind of question. It's like, did these collapse after the bone formed, or did it collapse kind of with the bone as it formed? And so that's kind of one of the big questions here is because globally we see for the most part magnetic fields are pretty strong.
Right.
And so it's a question, okay, well, did these stars kind of form with the bones at the same time? And I think that's an open question right now.
Very good. We'll come back to that open question business. Very cool.
Right.
Beautiful.
So for a lot of the rest of the paper, I maybe let's look at figure 16 very quickly,
Sure.
because we did try and
Heck.
quantify the polarization fraction, which we
Ooh.
haven't talked about for a little while now. But technically, it can be used as a probe of the polarization efficiency of the dust grain.
Okay.
So there you need to do it properly, you need more modeling than what we could do for this paper. This was really just a let's measure it and see.
Good thing.
And these power laws, essentially, the whole idea is that the
Uh-huh.
shallower the power index is, the more likely it is that
Yeah.
the dust grain alignment exists along the line of sight. And
Mm-hmm.
the steeper the polar law index is, the more likely it is that we're only probing the surface of the molecular cloud, for example,
It,
because the mechanism you need to get the alignment
yeah,
is
okay.
through starlight. And
Okay.
if there's too much extinction, the starlight just doesn't get through and you don't get alignment anymore.
Blocked. Okay.
So it's an important quantity for testing grain alignment theories and learning more about the physics of the dust grains.
Mm-hmm.
But yes, you need a lot more robust modeling
Well,
about
you
dust
guys,
grain physics to
you got to
really.
start somewhere. So this is
Yes.
a good start, right?
And so we
All
did
those data
that
points.
for
Oh.
yeah for all of the bones, and we also tested by changing the total intensity for density, and also checking that that we weren't overestimating the polarization fraction, because for some reason we were filtering large scale emissions. So
Oh,
we tested a different ways of doing that to be as thorough as possible.
okay.
Um,
That goes down to, okay, here are the other ones. These are
yeah.
the biased ones on 10, 24, and 47, 49. Yes. Wow, it's a lot of data points. Mm-hmm.
And that's every fourth vector.
Ah. Hey, you're data rich. You're data rich. Very
Yes,
good.
it was again a suggestion from the referee to try and clean this up. So
Yeah, we had a
thanks to
lot more
them.
points to begin with, like every pixel, and then like, there's a little too many pixels. So,
Okay. Setting down sometimes helps just with the understanding. Huh.
yeah.
Very
So
cool.
in the paper we discussed the meaning, the how meaningful these values are, and then when we go into the proper discussion, section 4,
Mhm.
we compare with some of the extragalactic sources. We kind of
You.
we
Yes. Mm-hmm.
yes, we try to reconnect the initial idea which was these bones are in the spiral arms of the galaxy. What do we learn about the spiral arms of our own galaxy when we compare them with others? And one of the most important comparison points was the SALSA survey by Enrique Lopez Rodriguez
Uh-huh.
as PI, but with their whole team, and they looked at different spiral galaxies with OCLOS,
Yes.
and and they often find the magnetic fields in spiral arms to be parallel to the spiral arms, which we sort of see with
Okay.
Planck, but it's a
Mm-hmm.
difficult thing to measure because
Mm-hmm.
since we're inside our own galaxies, and that was all the whole idea about the identifying the bones. The challenge of it was to try and we
Interesting.
see the galaxy, the plane of the we see the disk of the galaxy, but we don't. It's very difficult to know where the spiral arms themselves are, and where these objects
Yeah.
are. So that was I think there's a pretty good agreement, at least at larger scales, and then
Right. Bon.
the more you zoom in, the more it becomes complex. You have to worry about feedback and things like that.
Mm-hmm.
And that feedback might be important at galactic scales. You know, the star formation might
Some
help the
point there must be
dynamo of the
transition.
galactic magnetic field.
Yes.
So it's all connected. You know, it's all a big ecosystem in a way.
Right. Some point there's got to be a transition. Uh-huh. Very cool. Beautiful.
And yeah, the conclusions. We summarize everything we discussed in the past hour.
All good. It's all good.
um, and to conclude, I think it's a good idea to go to the last appendix,
Okay. That would be
which was
appendix
appendix.
I think.
It's figure 29.
Okay, let's looking for a quickie way to get there. Okay, let's just slide.
We showed the Spitzer images for one of the bones in figure one, but we did that for all of the bones. And I think it's really um, interesting to look at them, if only because they look great. But they also Spitzer is a really good way of seeing star formation, the effect of star formation, the feedback of it on the interstellar medium. So often when you look at the millimeter or far infrared, you're missing essentially that effect. You can measure it, but with the Spitzer images, it's extremely visual, right? You can see the H2 regions
Dang.
immediately.
Right.
It's just a beautiful data set
It's a
that
composite.
is
Yeah,
still
yeah.
useful decades after they were obtained.
Very cool. Got it.
And I think that's everything I wanted to go over. Is there something else you want to mention, Ian?
Yeah, well, I mean, the biggest thing is the data is publicly available, and so that's all.
Yay.
There's links in the paper. It's Dataverse. It's not just the data that's available. It's even a lot of the scripts for this particular
Yeah.
paper for what was used. Maybe Simon, you can talk even more about that. But
Yeah, and all the Python scripts that were used to make this paper are available, all of them. So if you've never worked with polarization data, but you wanted to try your hand at making these figures, you can
Mm,
just go get the codes on that Evers, the data, and just run them on Jupyter Notebook immediately, hopefully.
nice.
So that was a big emphasis of this survey, was really to have a legacy for the community,
Correct.
to be useful not just for us, but for anyone that would have scientific questions on the
In
making
the
field of
future.
these objects.
Uh-huh. Beautiful. And that's on Dataverse. I didn't find that immediately.
Yes.
But yes.
yeah.
Give a big shout out to Dataverse.
Mhm. Yep. And
Awesome.
and yeah, and so I mean, ultimately, just a big summary. The data is just great. It's rich. We n never have had a uniform, high-resolution magnetic field survey of these kind of big, huge galactic filaments that we had before.
Mm-hmm.
It bridges the gap between these large scale of Planck to
Uh-huh.
things that can be done at small scale. And so, uh, you know, I would hope a lot of follow up, will be on ALMA on these particular sources
Mm.
and
Yes. Yes.
things like that.
Yes.
And so, I think these bones definitely are the key building blocks to high mass star formation, how things just collect in the magnetized spiral potential. And so, I think it's going to help us test long-standing theories about not just filament formation, but just a whole, galactic simulations, how galaxies collect stuff in their magnetized spiral potentials and the role of magnetic fields. I think we're
Yes.
showing that you
Yes.
can't just do HD simulations. You need MHD, magnetohydrodynamic
Yeah, yeah,
simulations.
yeah.
You need the magnetic fields in there,
Hmm.
and ultimately, it turns SOFIA in a true legacy mission for galactic magnetism. We have this data here with public data products, and it's a long-lasting resource that won't be there won't be something like that at least for a decade, at least as far as I know. And it's something the community can use to study magnetic fields and the spiral potential, well beyond kind of these initial sets of papers that we have.
Hmm. Hmm. Awesome legacy. Awesome. Beautiful. Ian, Simon, I want to thank you so much for walking us through your very awesome APJS article. That was very cool. Most enjoyable hour I've almost ever had. How about that?
Well,
Sure.
thank
It was
you.
very good.
Great.
It was very good, really. It was really great. You guys did good with that. Let's see. You kind of touched on it a little bit here, and I'll just push a little bit on it.
Mhm.
And so where do you think we go from here, given the published article? And I'll let you pick the time scale on next. Is it, 1 year from now, 2 years from now? Is there additional data in the pipeline? Maybe on 10-year time scales, is there going to be another Sophia 2? Things along these lines. And so where do we go from here?
I guess just to begin with, we definitely have just an own group of some people still work on the data. We have a lot of people
Great.
working on both the simulation front of actually doing some galactic magnetohydrodynamic simulations. That's Rowan Smith's group and Jesse Marine on that. And then we have some people that are doing more kind of numerical calculations on or numerical models on bones and star formation
Ah,
and so that's more led by Phil Myers, just actually showing kind of like actually given what these bones and filaments look like, it seems like magnetic fields have to be important. And so I won't go too much into that, but we'll have more things working on the theoretical front based off these observations right away. So that's always great when your observations actually are motivating some theory. So that's
absolutely.
kind of the whole goal for a lot of these observations. There's just such a wealth of data. There's individual sources that can and will be done on these. There's already other groups that have published papers using the data that are in this program. So that's great. And so there's a lot more observations and I hope this is one of the legacy programs. Sophia is something that people will just be using for at least for the next decade. Maybe Simon, you can talk a little bit more about the future observatories.
Yeah, so unfortunately I don't think there's going to be a Sophia 2 anytime soon. One
Okay.
thing that we did learn with this experiment was that it's a complicated problem to have an airborne observatory, and complicated problems turned out to be expensive.
Yes.
But we do have alternatives, and I'm a big proponent of the Prima mission specifically.
Okay.
So
Yeah,
we're
yeah.
hoping very strongly to have a parameter in a far-infrared mission in space.
Uh-huh.
And with the latest technologies, MKIDS in particular, we can do observations at an unparalleled sensitivity. Uh, and get the magnetic field structure or just a polarization signal all across the sky. So some people suggested doing an all sky survey with the with Premat at essentially the resolution of Earth shell, and still be able to get significant polarization signal in a reasonable amount of time, considering the length of the mission.
Right.
So I think there's a lot of excitement for that. There's other observatories in the millimeter that do polarization. The RM 30 meter, for example, has their new camera being installed.
Mm-hmm.
There's CCAT in the southern hemisphere, the LMT in Mexico, and of course ALMA, which is going to have the wideband sensitivity upgrade in the next few years. And once that's turned on, it's going to help with continuum sensitivity tremendously, and that's what you need for polarization observations. So we might be able to map to mosaic a lot of these filaments, for example, with ALMA, and really get even higher resolution
Right. Drilling.
observations of these magnetic fields. So
Uh-huh.
it's going to be very exciting
Yeah.
on these fronts.
Yeah, it'd be really exciting over the next couple of years. both theoretically and observationally as we probe this very interesting aspect of, well, our galaxy and others, presumably. So very good. Awesome. I look forward to it. It'll be great. Simon, Ian, thank you once again for walking us through your very lovely article.
Thank you for having us.
Sure.
Thanks. Appreciate it.
Yeah. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.